Welcome to this lecture of Membrane. Today, I am Anissa from ITS. Chemical Engineering will be your master of ceremony. First of all, I would like to say a big thank you to Professor Toshinori Tsuru for your willingness to reschedule this lecture, and also for our moderator, Mr. Kusdianto, and of course, to all the participants for joining our guest lecture today. Okay, before we start the agenda, let me inform you some of the rules. That is, for all the participants, kindly turn on your camera if there are no network problems or else. And during the lecture, please turn off your microphone and only turn on the microphone when the moderator gives you a change. And for the participants, you can ask questions during the question and answer session by using raise hand feature or sending your question in the chat box. Okay, today's guest lecture will present a topic entitled Silicon-Based Membrane with molecular net sieving properties, that is application to gas and liquid phase separation, that will be delivered by Professor Toshinori Tsuru from Chemical Engineering Program at Graduate School of Advanced Science and Engineering of Hiroshima University, Japan. And also the guest lecture today will be by Dr. Kusdianto. Okay, on this special event, we have several agendas as follow: opening and continued by our main agenda, that is lecture from Professor Toshinori Tsuru, and continued by question and answer session. Okay, without any further ado, let's proceed to our main agenda that will be guided by Mr. Kusdianto. To Mr. Kusdianto, the time is yours.
Okay, thank you, Miss Anissa. Good morning. Good morning, Professor Tsuru. And good morning, the student. Today, I will be the moderator for the session. And first of all, we really appreciate for Professor Tsuru Sensei for your willingness to participate in this program, and also to reschedule the program because we have the problem in the previous meeting. So before we start, allow me to introduce the Professor Tsuru first. Professor Tsuru is a professor from the Chemical Engineering Department, Hiroshima University, and he received the bachelor, master, and doctoral degree from the Tokyo University. And then he was the associate professor in Hiroshima University from 1995, and then from the 2006, he is a professor in Department of Chemical Engineering, Hiroshima University. And also now, 2015 and 2017, Professor Tsuru was a vice dean of the Graduate School of Engineering, and also as a board member of the Society of Chemical Engineering Japan. Professor Tsuru, the research interest is about the preparation of inorganic and hybrid membranes, fused cell gel processing and atmospheric pressure, PECVD, and also sub-nanoporous membrane for gas, and then the membrane reactor. And also Professor Tsuru received a lot of the awards. The latest is the SGG Award from the Society of Chemical Engineering Japan. So for the student, maybe who interested about the membrane technology, maybe you can contact the Professor Tsuru for study abroad, master or doctoral student maybe. So maybe I will give the time to Professor Tsuru to deliver the lecture today. Professor Tsuru, time is yours.
Hey.
Oh, sorry, I will set you as the. Wait.
Pardon me?
Yes, Sensei, sorry. Okay, I already set Professor Tsuru as the co-host. So.
Okay, thank you very much, Dr. Kusdianto, for your kind introduction. First of all, I'd like to thank all the faculty members of the Department of Chemical Engineering of ITS, Surabaya, and also I'd like to thank the Anisha as a master of ceremonies. Thank you very much. It is my great pleasure to give a lecture as a guest lecture series of the Department of Chemical Engineer of ITS. Can you see my slide and the pointer?
Yes, Sensei.
Okay, good. Okay, today I'd like to talk about silicon-based membranes with molecular network net sieving properties, application to gas and liquid phase separation. Okay. So first I'd like to start my talk by giving general introduction regarding membrane technology and especially porous inorganic membranes, which is my major concern. And the second talk is now especially focused on silica and organosilica membranes with network controls with different techniques. And then move to the application in reverse osmosis and steam recovery and a brief introduction of membrane reactors. And I would like to finally conclude my talk. Now this slide summarizes my research activity of the group of separation technology laboratories, consisting of the 3 faculty members, including myself, also Associate Professor Kanesashi, Assistant Professor Dr. Nagasawa. Our team working on just on membrane technologies. We fabricate membranes, mostly metal oxide, such as silica titania, silica zirconia, hybrid oxide, and silica titania, and also organic, inorganic hybrid membranes, such as organosilicate. The technique is now solid processing or low temperature plasma. Here we have some typical cross-section of our membranes. Top layer is now made from silica networks, consisting of the SiO, siloxane bonding, making the network pores like this. Right? These membranes have been used for hydrogen separation and production. And these membranes also used for like other gas separation systems, like CO2 methane, hydrogen over organic gas, or olefin paraffin separations. We also work on power vaporization and vapor permeation for dehydration of organic solvent, alcohol such as IPA, ethanol, acetic acid, etc. And also we apply these kind of membranes for NF nanofiltration and reverse osmosis for aqueous systems as well as non-aqueous systems. I'd like to introduce these today. And also we apply this kind of inorganic membranes to membrane reactors due to the high temperature thermal stabilities. Now I'd like to start my talk by giving this slide. This was published in Nature 2016. As some of you may know these figures, these Professor Tsuru and the library pointed out 7 chemical separations to change the world. They are professors of George Institute of Technology, George Tech, and they point out very interesting figures like this. So this slide summarizes the total US energy consumption. It is 98 quad. As you can see, roughly 1/3 is used for transportation, automobile cars, and 1/3 is for industries. The rest is residential and commercial. We focus on these industries. Around 50% energy is consumed by separation process. This means the separation process is very much important. And the detail is now categorized like this. 40% is now distillation, 20% is drying, and 11% is evaporation. The rest, 20% is non-thermal separations. The Professor Shori and the library pointed out the membrane-based separation use 90% less energy than distillation. So which is a very huge energy saving is possible by membrane technologies. Among the membrane technology, the Professor Shori and the library pointed out 7 chemicals, right? Alkene from alkane, like a propylene from propane, and hydrocarbon from crude oil, uranium, greenhouse, CO2 or methane from dilute emissions, and the rare earth, benzene derivative from each other, like xylene separations, and trace contaminant removal from water. So to realize membrane-based separation to replace the thermal separation, we need to develop high-performance membranes. Also, we need to do some proof of concept experiment for energy savings as well as separation abilities. Now, this slide summarizes the membrane separation technologies. Membrane can be categorized in various viewpoints. In terms of the membrane materials, polymeric membrane is a major part of the materials. Our research team working on inorganic, like a ceramic and hybrid materials. From the viewpoint of the mechanism, the membrane separation mechanism can be categorized molecular sieving in the case of the porous membranes, and the affinity diffusivity mechanism for the case of non-porous membranes. So the pore size and the molecular size is very much important in the case of the porous membranes. In the case of the solution diffusion mechanism, the affinity with the membrane and the permeating molecule is very important, right? Now this membrane can be applied to energy issue. Pardon me? Huh? Is okay?
Okay,
Okay. So, this membrane can be used for energy, such as hydrogen or CO2 separation, and also environmental, like water purification and the seawater desalinations. Now, as researchers of the inorganic membranes, I would like to point out some advantages and disadvantages of inorganic membranes. Right? Inorganic membrane have a high thermal stabilities and also resistance to organic solvent, chemicals, acidic or alkali pH or peroxide. Of course, the mechanical strength and the long lifetime is very much important for inorganic membranes. Recently, more important point is the uniform pore size and high permeance and high selectivities due to the thin thickness and that control the rigid pore structures. Of course, we need to agree with a disadvantage, like difficult sealing and the construction cost is very expensive, but we try to develop a high performance membranes to overcome these kind of problems. Porous membrane, inorganic membrane can be categorized as based on membrane materials as zeolite, including LTA, MFI, forjacite membranes, and also metal oxide, silica, titanium, zirconia, carbon, metal organic frameworks. These membranes have a different type of pore structure, like a capillary type, granular type, especially typical for sol-gel-derived metal oxide like silica, titanium, and also slit-type pores of the carbonized graphene oxide, while crystalline material is now zeolite or morph-type membranes. Amorphous network is like this, prepared by CBD or sol-gel silica-type membranes. Of course, the surface chemistry is very much important to control the hydrophilicity and hydrophobicities. Our research teams has been working on silica-based membranes with this type of amorphous structures. We believe, this type of amorphous structure has a flexibility which will lead to less defect than crystalline materials such as zeolite and MOFs. And also in this case, pores are formed as the network space. So that's why I called this is molecular net sievings. So we need to agree that these membranes have pore size distribution, but we would like to say, okay, with high selectivities. Now I'd like to share with you some recent progress, our research activities, okay? Now, silica-based membrane can be prepared by sol gel and also plasma processing, which have the very advantage of thin film formation, which lead to hypermeas. Here we have the TEM cross-section of our typical membranes, which is published in 2021. This part is a substrate, alpha alumina substrate. These particles are now the particle of alpha alumina of the substrate. This was 1 micrometer, so that this space is a pores. Okay, on this substrate, we prepare alpha alumina particle layers. Here we have, you can see some small particles over here, which have the average pore size around 100 nanometers. On this alpha alumina particle, we further coated on silica zirconia intermediate layers, which have the pore size 1 to 3 nanometers, with the thickness is around 2 to 300 nanometers. On this intermediate layers, we further coat silica top layer with a thickness around 50 nanometers in this TM picture. And then this silica-based sol gel processing very much is simple. We adopt flash firing techniques, which requires only firing time of 10 to 20 minutes for each firing step. So it is very much productive method. More importantly, silica network can be sub-nanotunes in terms of the pore size to the hydrogen or CO2 of organic gas. And also, we can increase or manipulate the stability in the hydrothermal conditions. This typical network indicated prepared by tetraetoxysilane, Teos-derived silica networks. We reported ion doping. Since this silica network is flexible, we doped with metal ion such as nickel or cobalt to increase the hydrothermal stabilities. Anion such as fluorine is possible to be doped to make the SIF like this, to make the network loose and uniforms. We reported in 29 special techniques using bridged alkoxysilane. I will explain the detail in the next slide, which give also the loose structure, and then due to the C bondings, we have increased hydrothermal stabilities. Recently, we have started working on silicon oxycarbonate or silicon carbide to expect the hydrothermal stability. And quite recently, this year, we also reported the first paper on metal coordination systems to control the pore and the affinity with the molecules. Today, I'd like to briefly introduce all of our techniques. Now, before going to the details, I'd like to share with you the separation mechanism of the membrane technologies. As you know, the membrane separation can be possible based on sieving effect, left side, and then solution diffusion mechanism in the right side. Typical porous membrane is now, the mechanism is based on sieving effect. The pore size and also molecular size is very much important. And the non-porous type is now solution diffusion model. The molecules dissolve into the membranes and then diffuse to the permeable site and dissolve, so that the diffusion and then affinity is very important. Membrane performance can be evaluated with flux. Permeable flux is expressed with mole-based or cubic centimeter based. Most of this unit is used for the polymer people, and then this mole base is the inorganic researchers. And then this permeate flux across a membrane can be generated by the permeance multiplied by pressure differences. That is a driving force, the permeation of these molecules. Permeance, this P is called as permeance or permeation rate with this dimension, just divided by Pascal, it's a pressure difference. And then once you know the thickness of the membrane thickness, that you can calculate permeability. That is normalized with the thickness, okay? But in the case of the inorganic membranes, actual thickness is very difficult to measure. So usually we always evaluate the membrane performance with permeance in this unit, okay? And then this is a dimension conversion. 1 GPU gas permeation unit is often used for polymer people. 1000 GPU correspond to 3.3 10⁻⁷ mole. So if we have the 10⁻⁶, that is a high flux, okay? And to evaluate, this is a flux, okay? And then to evaluate selectivity, permeance ratio is very much important. Permeance ratio, I component and the J component is often called as permeance ratio or selectivity. And also, today I'd like to talk a little bit about the activation energy, okay? Activation energy is now typically obtained in these equations. In the case of the positive activation energy is now based on the Arrhenius plot, permeance increase this way. And then this activation energy indicates the energy barrier to overcome to permeate through the membranes, okay? Based on the membrane structure, like a porous to non-porous, the mechanism may be different from viscous, Nussen, surface diffusion, and the configurational diffusion. So we can always, use the permeance flux equation this way, permeance. Even for non-porous membranes, solution diffusion model, we can also use the permeance or permeability this way. So with activation energy. So always this permeance is very much important to evaluate membrane performances. Okay, so now I'd like to move to the details of my today's our research activities. So first, I'd like to share with you the concept of solid processing, followed by spacer method using bridged alkoxysilane, fluorine doping, aminosilica, and the metal coordination method. Then finally, I'd like to introduce the atmospheric plasma CVD. Now here we have the concept of our ceramic membranes prepared by solid processing. This SEM picture indicates some typical membranes cross-section. Again, the support. Here we have the 1 micron scale bar over here. There is alpha alumina particles. Some space is a pores of this support. On this support, a particle is coated like this to form the second layer. On this particle layer, we further coated the intermediate layer and the separation top layers. Here we have this membrane part is now ordinary outer diameter 1 centimeter and the length of 10 centimeter. This was connected with alpha alumina non-porous tubes, just a tubing, right? Now, this slide shows typical solid processing of membrane formations. Typical alkoxysilane precursor is TEOS, tetraethoxysilane, silicon with 4 ethoxide groups over here. This ethoxide group, OC2H5, is now hydrolyzed with water to form silanol groups. This silanol group further condensed to form the siloxane bonding so that we can make the network or some particles. Depending on preparation conditions, it is possible to make the colloidal sol, like nanoparticles or polymeric solute, which give us the linear-like inorganic polymers. These so can be coded on the support. In the case of the colloidal solute, just several nanometer, so the pores are formed as space among the particles, so which is suitable to fabricate nanopores, such as titanium or silica zirconia, to fabricate ultra or nano filtration membranes. In the case of the polymeric solute, we coded on the support. Pores are formed as network pores, like this way, right? So which give the micropores. But in the case of the silica or organosilica, this system is now suitable for gas or PV or power evaporation or reverse osmosis. Now this slide shows how we prepare the membranes of silica or organosilica membranes, right? So now we use the porous alpha alumina support, and then particle layer is now formed, and then we coded the silica zirconia intermediate layer, which has a pore size 1 to 2 nanometers. On this intermediate layer, we coded the silica-based salt. Okay, and then fired at different temperature, and then we can get the silica-based membranes. This is the typical procedures. Now, we propose spacer techniques using bridged alkoxysilane 2009, relatively recent. Typical bridged alkoxysilane is bis-tolyetoxycylyl ethane. This precursor have 2 silicon atoms as ethane as this linking unit. This linking unit is stable in hydrolysis and condensation reactions, which stay in the network even after firing at 300 degrees C. So we expect the pore size can be tuned to this linking unit, just the minimum unit, like a Lego, right? So now we fabricate membranes using TEOS BTESM with a methane as a linking unit and ethane as a linking unit. Here we have the permeance plotted as a function of kinetic diameters of TEOS-derived BTESM methane-derived and the BTESE ethane-type derived membranes. When you look at the permeance ratio of hydrogen over nitrogen and summarize over here, TEOS-derived membranes show more than several hundred times differences. Hydrogen is more permeable than nitrogen, okay? But by changing the precursor from TEOS to BTSM, BTSE, you can see increased permeance. Okay, more than 1 order magnitude permeance increase for hydrogen. But when you look at the hydrogen over nitrogen selectivity, the selectivity decrease from 600 to 60 and around 10. But this BTESE derived membrane still keep the high selectivity of hydrogen over SX6, which is the largest size of the gas, 5.5 angstroms. So we would like to say, okay, there is no pinholes in the case of the BTSE. So this decreased permeance should be the controlled pore size. Now this is the trade-off of hydrogen over SX6, okay? So this is called as trade-off, okay? So selectivity permeance ratio is plotted against the hydrogen permeance. Of course, higher permeance and higher selectivity is a good way for good membranes. Here we have just some plot collected from the literature together with our membrane is plotted over here with a conventional silica is a square case and a CVD triangle, also zeolite membranes and also triangle and a diamond over here. You can see our BTEC derived membranes show very high permeance, higher than 10-5, and also high selectivity of more than 1,000. So we would like to conclude, okay, we successfully control the silica network by using bridged alkoxysilane as a spacer techniques. Now this is slide show the some temperature dependence of the organosilica membranes, right? In the case of the helium and the hydrogen, almost a similar curve trend. By using a different linking unit, methane over here, ethane, propane, hexane, and the octane over here. And the benzene is expressed with a square case over here, okay? And then we get the activation energy, okay, for each membrane, and summarize this way, okay? So this is summarize the link effect of the linking unit of the permeation properties. Helium over hydrogen, okay? The size of helium is now 0.26 nanometer. Hydrogen is now 2.89 nanometers. So this selectivity indicates the index of the pore size, okay? Higher selectivity indicates small pores. Small selectivity indicated larger pores. As you can see, with the increase in the carbon number, permeance ratio decreased, right? So this indicates pore size increased. Now, when you look at the right side figure, with the increase of carbon number, activation energy of hydrogen increased, okay? The activation energy is now indicated as a slope of the Arrhenius plot. This it suggests the non-porous membranes, okay? With the increase of carbon number, activation energy increase. Now, this is a summary of the pore structure and the permeation properties. We change the linking unit, methane, ethane, propane, hexane, and the octane, okay, in the carbon number. We measure BT surface area of the this powder, measured as powders derived from each soil. This indicates the highly porous for BTSM and the low non-porous for large number of the carbons, which indicate some pores are plugged with the linking unit, right? In the case of the membranes, we have a low activation energy of the small linking unit and large activation energy, like a large activation energy for large linking unit, indicating, okay, in the case of the small linking unit, the mechanism is based on the pore size. It is just a molecular sieving mechanism. Rigid and the small pores can allow the low activation energy like this, and then high carbon number, which is more like close to this, polymer membranes, which is now the activation energy is now determined by thermal vibration of the network with a linking unit. Now move to the fluorine doped silica. Okay, this simple is now the simple. Okay, just we add the ammonium fluoride into the tails, and then hydrolysis and condensation. We have the fluorine doped silicon soil coating on silica zirconia intermediate layer to have the fluorine doped silica membranes. Here we have the permeance against the permeance molecular diameters. This is a fluorine, no fluorine, that's a pure tails, fluorine 10%, and 20% over here. Again, permeance of hydrogen increased by adding the fluorine 1.3 to 2.3. Also, nitrogen selectivity decreased. Still, we can keep the high selectivity of hydrogen over SF6, more than 1,000. Now, this was confirmed. We believe this, the by fluorine dopings network is increased. This was further examined by measuring the FTIR. We can see by doping fluorine to 0, 0.51, and 2, we can see some of the blue shift of this siloxane bondings, and this indicated this SIO bonding is now becoming large bond angles, making the more loose structures. This also summarized the trade-off of hydrogen over propane and hydrogen over propane, propylene, propane. okay, of our membranes. You can see the propylene is now smaller size than propane in the size. So selectivity is larger for hydrogen over propane. When you look at the hydrogen permeance, it's very large with high permeance 10,000, 1,000, with a permeance is several 10⁻⁶. When you look at the up boundary layers, you can see C1 linking unit and the C2 linking unit is now show the very high permeance and the selectivities. This is a trade-off of CO2 methane and the propylene-propane separations. Reportedly, the zeolite membranes such as DDR or SAP34 CH chabasite type membranes are plotted over here with a triangle and also square keys show very high permeance ratio and then permeance for this type of membranes. Our fluorine-doped silica membrane is plotted over here, almost show high perm selectivity similarly to zeolite membranes. Right side figure indicated the propylene-propane separation. That is also very important systems to be separated and required huge energy to separate these cross boiling point mixtures. So here we have the some point is the zeolite membranes and also ZIF type membranes is plotted over here. Especially ZIF type membranes show very high selectivity. Okay, with the square keys over here, ZIF8 type membranes. Our membrane is now plotted over here. Especially the star key is now fluorine-doped silica, and also this circle key indicated by organosilica membranes. Again, these membranes show very high selectivities and permeance. Now, also we have work on amine silica membranes. After a series of experiments, we categorize amine type alkoxysilane as unhindered amine and also hindered amines like this. Unhindered amine is now primary amine, and also secondary amines. And hindered amine is like a tertiary amine or pyrimidine types, where the CO2 can directly access this kind of amine functional groups. On the other hand, hindered type amine cannot. Direct contact with amine and the CO2 is a little bit difficult, is hindered. Right? And also we have worked on network control via hybrid with amine type alkoxysilane with non-amine alkoxysilane, such as BTESE or TEOS types. Now I'd like to share with you some results. Here we have a trade-off of CO2 nitrogen separation. Perm selectivity is now plotted against CO2 permeance. This pink area indicates unhindered amine. Blue indicates hindered amine type over here. As you can see, selectivity is higher for hindered amine. Okay, permeance is also higher for hindered amine. Right? Even hybrid with amine types with the BTESE indicate very high permeance close to 10⁻⁶ with enough selectivity of CO2 nitrogen around 20 or 30. So this was analyzed based on activation energies. In the case of the activation energy of CO2 and the nitrogen is now plotted against the CO2 activation energy over here. Unhindered amine over here, it is very close to zero. It indicated unhindered amine type, primary amine and secondary amine, CO2 and the nitrogen activated in similar way. On the other hand, hindered amine, activation energy CO2 minus nitrogen is now becoming negative, which indicated that activation energy of CO2 is smaller than nitrogen. So it is important to control the diffusivity and the affinity with the membranes. Now, Quite recently, this year, we proposed a metal coordination to amine for pore size control. This was proposed by one of my PhD candidates who graduated from ITS. I'd like to introduce her later, okay, in the last part of my talk, okay. Previously, I introduced the spacer method, okay. This kind of the changing the linking unit, the membrane material is becoming porous in the small linking unit and dense or non-porous for large linking unit. She proposed use the bis-trimethoxypropylamine BTPA like this. There is a secondary amine over here. With this membranes, it is non-porous, okay, due to the large linking unit. But this amine group work as Lewis base, okay? And then she proposed a doping metal ion, such as transition metal, like a nickel, zirconium, zinc, copper, etc., as a Lewis acid. So she expect there some coordination between metal and the amine groups, which give the rigid linking unit, and then finally move to the microporous materials. Here we have the data of the effect of the metal ion. In the case of the pure BTPA, silver dope, copper dope, nickel dope. This table summarizes the surface area with a doping amount, doping species. As you can see, also the same amount mole ratio was doped. Nickel is most porous. So this suggests nickel is now strongly coordinated. Okay, this coordination was confirmed by using the XPS and also UV spectra. This is a case of the pure BTPA. And then after doping nickel, so the shift was observed. Right, the UV spectra indicate this is a case of the pure BTPA. This is a nickel nitrate. We observed new peaks, right? So this suggests coordination occur by doping with the nickel nitrate. Now this is a case of the nickel amount effect, okay? By increase the nickel amount 1.25, 0.25, 0.5, okay. Surface area almost increased linearly with the doping amount. This also confirms the coordination may induce the formation of interparticle pores. This is the summary of the trade-off of the nitrogen over SF6 as a function of nickel permeance as trade-offs. Okay, so nitrogen is a size of 3.6 angstrom, and then SF6 5.5. So this is a good index to form the relatively large pores. Okay, these circles indicate BTPA doped with metal, and then other point is now collected from the papers from the polymer or zeolite, okay, etc. Okay, this is the types of metal, and this is the amount of the nickel dopings. As you can see, our metal doped membrane show very high selectivity of nitrogen over SF6, also high permeance. So we apply, okay, we believe this membrane have relatively large pores, and then we apply these membranes to PB separation of non-aqueous mixtures, such as methanol, toluene mixtures, okay? We skipped the data today, but these membranes show high separation factor, higher than 10,000 with high flux, and also very stable performances. Now, also we work on silicon oxycarbonate or silicon carbide type membranes prepared by polycarbonylene, PCS, or polystyrocarbonylene, TIPCS. And also we work on allyl hydroperoxycarbonylene, AHPCS. These precursors are thermally cross-linked to form the SIC network. And so we expect this SiC network very stable in high temperature and also steam atmospheres. Now here we have some of the permeance are plotted as a function of the molecular size of these gas, right? So you can see hydrogen show very high permeance, higher than 10⁻⁶, with a very sharp selectivity of hydrogen over other gas. Now I'd like to briefly share with you some of the separation systems of hydrogen over propane, mixed single and the mixture, using the membranes of PCS, polycarbosilane type membranes. Okay, in the same at the 500 degrees C. You can see this is single and the mixture. You can see the hydrogen permeance is higher than 10⁻⁷. Also, hydrogen over propane is now higher than 1,000. So we can get the high propane purity of 99%, right? Now let's move to the, okay. Today I introduced some techniques of silicon-based membranes in terms of the ion dopings and spacer techniques, and also SiC type membranes over here, and also metal coordinations. Now I'd like to also add one more techniques of atmospheric plasma CV techniques or low temperature synthesis. Okay, in the plasma, ions and the radicals are formed in high density at low temperature in atmospheric pressures, so that in the plasma discharge region, precursor can be activated by plasma even at low temperature. So this enable film formation at low temperature in the dry process. Atmospheric plasma indicate high density. So high density indicate first synthesis. And also atmospheric pressure is very much easy to scale up to the large surface area. You can see atmospheric, you can touch the atmospheric low temperature plasma in this way, like this. Also, we can use the atmospheric plasma like this kind of the jet type membranes. So we can make the membrane on this substrate, like in this jet type. Also, we can also make the membranes in the direct deposition inside the plasma region. Okay, we put this is a substrate over here inside the plasma regions. Here we have some of the typical helium permeance and also permeance ratio as a function of deposition times. Okay, as you can see, after 2 minutes, okay, membrane reach steady state, so that we say, okay, ultra fast synthesis of this type of membranes. Cross-sectional view indicate only 13 nanometer of the top layer, okay, with high permeance higher than 10⁻⁶, with hydrogen over SF6 selectivity more than several hundred. Okay, so this type of plasma membrane is after treatment of 300 degrees C, which give us the very high selectivity of CO2 methane, like higher than 100. So it is very much promising. Okay. And also, I'd like to share with you some more applications, right? Like first, reverse osmosis. Okay. Now, 2011 to 2017, I was a PI, principal investigator of CREST, Core Research for Revolutionary Science and Technology, which is a large project supported for 5 to 6 years. The title of my project was Development of Robust Reverse Osmosis NF nanofiltration membranes for various types of water resources. The purpose is now chlorine resistance and also thermal stability of reverse osmosis and NF membranes. Now, this is a typical, okay, now, actually, we work on both polymeric membranes as well as the inorganic membranes. Here we have the typical result of organosilica membranes. This curve shows the rejection as a function of a molecular weight of the different organic solute, like methanol 2, IPA, butanol, glucose, etc. Membranes were fabricated from BTSE, SN linking it. This SW30HL is a typical reverse osmosis membranes commercialized by Dow Film Tech over here. Our membranes show almost similar molecular weight cutoff curves with conventional reverse osmosis membranes, with a molecular weight cutoff 100 to 60 Dalton. And these membranes were evaluated in the robustness. This indicates chlorine tolerance membranes. Okay. Now the rejection of BTSE derived membranes and also rejection of SW30HL are plotted as a function of chlorine exposures, ppm hours. After contact with the chlorine, for the case of SW30, this shows decreased rejection. This indicates degradation occur in the case of the SW30 membranes, while our membrane stays stable even after contact with the 35,000 ppm hours. The right side indicates the hydrothermal stability of our BTSE membranes. Okay, experiment was started from 25, and then temperature was increased 40, 60, 80, and then back to 25 degrees C. You can see the almost similar water permeance 25 degrees C, even after 80 degrees C for several 10 hours, and the rejection was kept. So this indicates our membrane is robust to chlorine and high temperature hydrothermal conditions. Now this membrane was used for aqueous systems. Now I try to extend this type of membranes to organic mixture separations. So first, to evaluate the separation ability, we calculated the energy requirement of distillation and the power evaporation and the reverse osmosis. As you know, the distillation comes, okay? Feed liquid is separated by reboiling the liquid from the bottom with a reboiler, and then the evaporated vapor was condensed on the top in the condensers. So we need heat in the reboiler, and then heat must be removed from the condensers. And then, as you know, the reflux is very much important in distillation columns. To calculate the energy for in the case of the distillations, okay, distillation energy can be expressed with this way to indicate the heat in and heat out, and the latent heat of vaporization lambda with the reflux ratio of FR, and then also the flow rate of distillate D. This is the energy requirement of distillation columns. In the case of the PB, okay, PB allows the only selective permeation after vaporization and the condensation. So this corresponds to the reflux ratio of 0. Okay, so this indicated the 2 lambda D. In the case of the reverse osmosis, no phase separation occur, no heat for vaporizations. So we calculated the energy for reverse osmosis as a sum of the minimum energy of separation, and also excess energy is important to drive the separation, okay, which indicated D multiplied by the excess energy for reverse osmosis. Now here we have the typical result of the mixture separation of 0.5 to 0.5 of mixture is separated to purify the A component and the residue. Okay, energy of recovered A component is now plotted as a function of recovered A ratios. As you can see, distillation column is now depend on the reflux ratio is 2 to 10. But if you look at the PV, it's almost 1/10 of the distillation columns, and then reverse osmosis, almost 1/100th of the PV and also distillation columns, which indicated the huge amount of energy saving is possible by using reverse osmosis. So realize these systems, we evaluated the organic liquid separation, okay, in reverse osmosis. Okay, in this case, we applied BTESA, acetylene type linking unit, to separate the organic azeotrope mixture, methanol DMC, dimethyl carbonate, methyl tertiary butyl ether from MTBE. Okay. In reverse osmosis, both phase are liquid phase and the par evaporation. The feed side is liquid phase and the permeate side is vapor phase. Okay, and then we compare the performances. Now here we have the reverse osmosis of methanol tolerance systems. Okay, so experiment was started from 8 megapascal, 80 bar. Okay, and then increase 12, 16, and then back to 8, 18, and 8 megapascal. This blue key indicate separation factors. As you can see, even after 18 megapascal, 180 bar, the membrane was stable. Okay, this membrane is actually robust in high pressure. The right side indicates the long-term stability test. Even after 60 days, which was immersed kept in the liquid phase, the membrane still show high performance. It's also similar performance with the beginning. So we believe this membrane is stable in long-term stability. Okay. Now this slide indicates the reverse osmosis of the time course of different solvent. This is a case of the methanol MA, methyl acetate, and methyl DMC, methyl dimethyl carbonate, and the methyl MTB, methyl tertiary butyl ether, like this. Okay, as you can see, high selectivity was achieved with large molecule. MTB indicated more than 99% rejection. Okay, and then even after 12 megapascal, okay, the membrane was shown very stable as a long times. This indicated 1,040 minutes. Okay. Now we move to the comparison of the reverse osmosis and the PB separation performances. So now we know first this membrane was initiated from PB. Okay, from the 100% of methanol, 90, 70, 80, and then 30 to 110, and then back to 100 again, pure methanol. On the right side, followed by experiment reverse osmosis. Okay, exactly the same membranes was used for methanol DMC separation in power evaporation and reverse osmosis. Okay, and then we try to analyze these performances. Okay, by analyze to analyze the performance, we use generalized solution diffusion model. Okay, which I proposed actually in the 1991, almost 30 years ago. Okay, now we apply this model. Okay, this generalized solution diffusion model is based on the chemical potential difference is a driving force of membranes, and then diffusion occur through the Fickian law. Okay, so but anyway, this number one is a very simple Fickian law, like a permeation rate is now decided by the diffusivity and the thickness, and then concentration differences inside the membranes. And then this number two and number three indicate chemical potential equilibrium in the feed side and the permeate side. And then this was formulated in this way: reverse osmosis and then power evaporations. Interesting point is the PB and the reverse osmosis is now indicated using the same K, okay, with the same activity in feed and the permeate side. Feed side is the same, right? So K is the activity normalized permeance, which is the intrinsic properties which can be decided by diffusivity of the membranes and the component of concentration in the membrane, activity in the membrane, and the membrane thickness. Now this was shows a comparison between reverse osmosis and then power evaporation in the methanol concentration in permeate and also total flux. As you can see, these points are experimental data. PB always show high permeate concentration, okay, more purified in PB than RO, and the flux is more than 10 times higher in PB, right? But based on the model, generalized solution diffusion model, even same K gives a curves, okay? So we are successfully predict, okay, by using the same K for PB and RO with the same K values. Now this slide summarizes the trade-off of the methanol DMC and the methanol toluene trade-off in terms of this reverse osmosis, and then this part, the pink part is PB, okay? With other membranes like a silica zeolite ZOF type membranes, in most of the membrane, all of the membrane, other membrane in just power evaporations, okay? As you can see, organosilicon membranes show very much high performance together better than other type of membranes. Also, these reverse osmosis and then power evaporation was successfully predicted by solution diffusion model. Okay, now, okay, move to a little bit different topics of steam recovery. Okay, almost 1 hour, so I need to rush. Okay, now organosilicon membranes have like this, okay, linking unit, which show very high performance in the hydrogen over SF6, and also, okay, this membrane also show a high performance for acetic acid dehydrations. So organosilicon membranes show, okay, high molecular sealing, high permeability, and high hydrothermal stability, and stable against acid. So we apply these membranes for steam recovery, okay, selective removal of water vapor from steamed gas. Now here is a trade-off of hydrogen over water vapor over hydrogen, and hydrogen over nitrogen. Okay, so this membrane, organosilicon membrane, is plotted over here and over here, right? Other type of membrane, like a Nafion type polymer membrane, is now typical water removal membrane. The Nafion in polymeric membranes is plotted over here. Organosilicon membranes show very high performance even at high temperature, 150 to 300 degrees C, with a permeance higher than 10-6, with a selectivity around 100 for over hydrogen and over nitrogen, more than 1,000. Okay. Now we also propose the increased hydrothermal stability of BTSC derived membranes. Okay. Now, you know, as I explained you, intermediate layer was prepared by silica zirconia, but we proposed the use of colloidal so BTSE as the intermediate layers. Here we have some result of the stability issue as a function of times more than 300 hours. Conventional BTSE membranes coated on silica zirconia show decreased water permeance, but BTSE coated on IBTSE, intermediate layer, is hydrophobic one, so very much stable as long as 306 hours, with, of course, high selectivity of water vapor over nitrogen. Now, this type of membrane is now under proof of concept experiment for the steam recoveries. The concept is now production of water from gas phase. Here we have the typical incinerator. Waste is now combust with air in the this incinerator, and then exhausted gas should be cooled down with the sometimes injection of water liquid to cool down this gas, okay? And then usually exhausted from the smoke stack. So we propose the use of membranes in the process, okay, to recover steam. Recovered steam is now, okay, now re-inject into the, for gas cooling, okay? And then this removed water steam is now in this line, is now prevent the white smoke from the exhausted gas. And also we are able to recover the latent heat. Okay, this research is now under the performed in the, is now under proof of concept, okay, supported by environmental research and the technology development fundings, okay. Also, we briefly expressed there some application to process intensification by membrane reactors. In the chemical industry, reaction and separation is very much important, and then usually operated in the different units. Membrane reactor combine this reaction and the separation in one unit so that we can get a very simple and a compact configurations. More importantly, this membrane reactor combined system can change the equilibrium. Typically, okay, methane steam reforming. This is under equilibriums. By removing hydrogen from the systems, the reaction moved to the product side based on the Le Chatelier principle. This is a list of application to membrane reactors for the last 20 years, mostly hydrogen production, such as steam reforming of methane, ammonia dehydrogenation, and then organic hydride dehydrogenation to produce the hydrogens. These ammonia and organic hydrides is very much promising as energy carriers. Okay. Also, we work on sulfuric acid decomposition to produce oxygen. And quite recently, okay, next year, 2022, we will publish one paper on trans-esterification reactions. And that is also very much interesting to remove methanol from the systems. Now, I'd like to conclude my talk, okay, organosilicon membranes with amorphous structure show high performance and high selectivity in the gas and liquid phase separation, and then promising for future applications. Of course, this is the last slide for my actual presentation, but I'd like to share with you some of the introduction of Hiroshima and Hiroshima universities. Hiroshima is located western part of Japan, much western than Tokyo and Osaka. We have a world heritage like an atomic bomb dome, like this. Also, Itsukushima Shrine. You can see this is a red gate on the sea, and there's some shrine on the sea. That's very beautiful. We have a full deep nature, like a mountain and a river, and then sea and a beach. And we enjoy the professional sport, baseball, Hiroshima Toyo Cup, also football and handball, etc. Regarding the Hiroshima universities, we have the student, more than 10,000 students for undergraduate and graduate. And we have more than 1,000 faculty members and staff members. Hiroshima University ranked 9th among the 90th national university in Japan. We have 11 college and 11 grad school. Actually, I belong to engineering chemical engineer. Actually, if you are interested in studying in Hiroshima University, please don't hesitate to email to me. Okay. As a really last slide, I'd like to share with you some information from PhD candidate, present and former from Indonesia. First student was Dr. Sofitam Anisha. She actually graduated from ITS. She joined my laboratory 2016 to 2019, and then followed by postdoc with me. And then now she got the job in some researcher in some Japanese company, membrane manufacturer company. She published the papers with me at this Journal Membrane Science, Journal of Solvent Science and Technology, Separation and Purification Technology, another one, and also JMS again, and also Separation and Purification Technologies. Now presently, I have one student from Indonesia. She graduated as a BS Department of Chemistry of ITS and also MS. And she is now work as a lecturer at University International Zeeman, Indonesia. And then she joined the lab in 2019, 2 years ago, right? At this, so far she published, the first one is now 2021, January or February, selected as a cover art of Materials Chemistry Frontiers. She worked on metal-induced microporous aminosilica membranes. Another paper is ACS Applied Materials Interface, so 2021, and also Journal Membrane Science 2022 next year. Okay, this is okay. That's last slide. I like to acknowledge, thank my colleagues and also my former student. Also, okay, these are some photo of my student. And also, I'd like to thank all of you for your kind attention. Actually, this is the second time rearrangement. Thank you very much for your kind of participation. I'm very happy to answer any question. Thank you very much.
Thank you very much, Tsuru Sensei, for the nice presentation from the general introduction about the membrane technology, and then silica and organosilica prepared by the liquid phase and gas phase, and also the application of this fabricated membrane. So no time for the question discussion. If you have question, just please raise your hand. Any question? Nurdiana Ratna Sensei. Okay, Nurdiana Ratna.
Thank you for the opportunity before, and thank you, Professor Tsuru, for the explanation. I'd like to ask two questions actually. And I was wondering about the one slide you have explained about the atmospheric plasma CVD. And I look in the symmetric diagram, there is two methods which we can make the membranes in upper side of substrate and the other is inside of the tube. So I was wondering which method is easier and gives the best result in this case. I mean, like for the separation or membrane produced like that.
Are you talking about this one? This is
yes,
also prepared inside. Okay. Membrane can be prepared by outside, okay, and also this second one also prepared. Just membrane is formed always outside surface. But the plasma is now this case. Okay, plasma is discharged this way, right? So the CVD occur just after contact with plasma subject, okay, and then. This system substrate is put into the some tubes, and then discharges occur outside. So we always fabricate the membrane outside surface. But the membrane is now like this is now inside, like an in situ direct deposition, right? This is just like a painting, right? So this painting method is more easy. Okay.
Okay, I got it. Thank you. And can I ask one question?
Well, sure.
About the hydrothermal stability test in your site? There are line that is not reaching the same time. I mean, like the line is shorter than the others. So is that mean the membrane is broken or something? I mean, like the membrane cannot continue the test. Sorry, sir, I am confused about that.
I talking about which one? Actually, the hydrothermal stability of the gas phase, vapor.
I think it's one.
This one.
Yes, this one. Yeah.
This one. Okay. Yeah. This case actually we have not examined in the details, but we believe, okay, silica zirconia. This is an intermediate layer which has a pore size 1 to 2 nanometer. And then this membrane is coated on silica zirconia. What I guess is now, silica zirconia layer is not so stable as IBTSE. IBTSE hydrophobic. Okay, so silica is a free silica, hybrid of silica and zirconia. Zirconia should be stable in high temperature and even under hydrothermal conditions, but the silica is not so stable. Okay, so this silica is somewhat decomposed, okay, dissolved in water phase, and then migrate to some small region, and then making some layer of the dense layers. So that's why the permeance decrease with times. But in the case of the IBTSE, this is a IBTSE intermediate layer BTSE. The size is now actually the 1 to 2, pore size is 1 to 2 nanometer over here. And the BTSE layer is now 0. Say 5 nanometer or something. Separation layer is coded, okay, this top layer, right? So in the case of the silica zirconia, this intermediate layer was degraded. This IBTSE layer is stable, okay, this is a IBTSE stable. BTSE itself stable, okay? This BTSE, okay, stable. Silica zirconia, okay, this so decrease the permeance. This also decrease. So the difference of this BTSE coded on IBTSE is now stable. The difference is this intermediate layer. Top layer is the same. So top layer itself, BTSE is stable at high temperature in 200 degrees C, even under steam, right? But the difference is just this intermediate layer. That is our understandings.
I think I got your explanation. Maybe that's all of my question. Thank
you.
Okay,
thank you, Ben. Okay, yeah. Thank you.
Ratna. Okay, and then for the next question. Oh yes, Sensei, I'm sorry. In this 2-day lecture, not only the bachelor student join this lecture, but also some graduate student like Nurdiana Ratna. Nurdiana Ratna is a master student, MEC, yes, MEC.
Okay, yeah.
Okay.
Yeah.
And then next question, Mevlana. Mevlana, please.
Yeah, thank you. Good morning, Mr. Tsuru.
Good morning.
Yeah, it is very awesome to use silica on membrane, and I think must be good for future high technology membrane. May I know your foresight about silica membrane in the future? Can it be the trending one among all types of membrane? Yeah, can it be the trending one among all types of other membrane?
Could you repeat the question, please? I cannot catch.
May I know your foresight about silica membrane in the future? Mr. Suru?
Future, yeah. Yeah, I think, you know, this is a membrane of BTEC, organosilica membrane, okay? This is now under the proof of concept experiment supported by these fundings. I hope this type of membrane can be commercialized very, very soon.
I see.
Mhm.
And then may I ask one question more?
Sure.
May I know what is the best country which has good mining in silica for supplying this raw material for the membrane? Mr. Suru.
Your commercial application of the silica membrane, your question is now,
The best country which has good mining silica for export to
export the membrane?
to
Uh,
raw
uh.
material of the membrane, or does Japan import this, or does Japan import this type of silica or making itself?
You're talking about some
The
precursors or
precursor,
membrane?
Sensei, yes.
Precursor,
Yeah,
precursor,
yes, yes.
okay. Precursor, maybe, I'm not sure. Silica is probably the most abundant chemical species all over the world, probably. I'm not very sure which country is most suitable to fabricate, you know, silicon materials. But yeah, silicon is now mostly used as semiconductor. So yeah, I'm sorry, I cannot answer very well. Yeah, but yeah, the two purified silicon precursor need a lot of energy, probably. Yeah.
Okay, Mr. Suru, thank you.
Yes, Sensei, because maybe like Nordiana Ratna use not TEOS as the precursor, but using the water glass, because water glass is quite cheaper, is quite cheaper compared to the TEOS as precursor, Sensei, yes.
I have never used the water glass. Always we use the tetraethoxysilane.
Yes, okay.
So yeah.
Okay, maybe the next question. If you have the question, just please raise your hand. No, we are waiting for the next question, Sensei. Maybe I have the question, Sensei. In the
Sure.
maybe your the presentation, the one application of the membrane is can be spared from steam reforming. So CO2 and the hydrogen.
Yeah.
So how does it work, Sensei? The membrane can separate the hydrogen and also the carbon dioxide because both are the gases, right?
Yeah. So this actually is one typical application of the hydrogen separation membrane in this case. Okay, the case of the steam reforming. Okay, methane and the water react to produce CO2 and hydrogen. Okay, so usually this equilibrium conversion is limited by the equilibriums. So to have the higher conversion, okay, this reaction should be operated at maybe 800 or 900, but by removing hydrogen, okay, not the CO2, so only hydrogen is removed. So if you have a very small pulse, you can shift this reaction to the the product streams. So you can also reduce the reaction temperature from 800 to 500 degrees. It is a dramatic, energy saving or cost reduction of the chemical plant. So yeah, usually our membrane is now only remove or extract hydrogen from the systems.
What is the average size, pore size, Sensei, for the membrane?
For separation of hydrogen?
Yes.
Yeah, size should be around 3 angstroms. The CO2 size is now around 3.2 angstroms. The hydrogen is 2.89. So the pore should be between the two species.
Oh, okay. Okay. Thank you, Sensei.
So
Okay,
in this case, more easy. So organohydride, okay, the hydrogen is now 2.89. Toluene and the methyl cyclohexane is larger than 5 angstrom. More easy
Yes,
to
yes,
separate. Yeah, this system, right?
yes. Yes.
Mm.
Okay, thank you, Sensei. Okay, for the next question, for the student, please raise your hand because the topic is very interesting. Okay, Sensei, maybe waiting for the next question. I still have maybe one question. As Sensei explanation about the fermion and the carbon number. So at the early state, it decreased significantly, Sensei. After that, this is just a level up. So would you please explain why at the early state at the lowest level of the carbon number, it is decreased significantly, Sensei?
This one?
Yes, this one, Sensei.
Actually, the helium over hydrogen. Okay, this is now the size of helium is 0.26, and then helium is 2.6, the smallest size, and the hydrogen 2.89 nanometers. So actually, the carbon number 0. Actually, this is just like a Theos derived membranes. We can fabricate membranes with small pores without linking in it, right? So with adding some of the linking in it, pore size, network pore size would increase, okay? So that which allow the higher permeation of even hydrogen, so that the perm selectivity decrease a lot this way. So we concluded the pore size increase by increase the carbon numbers. That is the some concept. And then, there is actually, when we propose the spacer method, this is what we expect, this trend.
Okay, thank you, Sensei. Next question will be the Miss Ayu. Miss Ayu, it's your time.
Thank you for the opportunity, Mr. Kusdianto. So I want to ask about the sol gas processing for the membrane fabrication. So in your early slide, in the sol gas processing for the membrane fabrication, there is the two methods that can be used. That is the colloidal and polymerics. I want to ask about which type is the best way or the most preference. As I know, the solvent for the membrane fabrication, it needs many solvent. Is this one of the consideration to choose the best method that can be used?
So making the solvent, you asking which type of solvent I used for making the salt?
Type of the method that is the best. I think in your early slide, there is a colloidal and polymeric.
Yeah. So usually we use the water-based and alcohol. Usually water plus ethanol is used to fabricate the hydrolysis and the condensation reactions. Only water, this is kind of an oil. So this BTS is just like a droplet if we just add it in water. So we need some ethanol as a solvent, making the homogeneous mixing, right? Yeah. So yeah, usually ethanol is the best, my feeling is. Okay.
Is there any other consideration to choose this method, sir?
Could you say again?
Is there any other consideration you are using this method?
Yeah. So this method, I mean, fabricate membranes, including the most important point is actually the soil is very important. We always have a very clear soil. If actually the coating process is now like a we need to have a homogeneous soil, even nanoparticle case and also polymeric soil case. So try to fabricate a uniform cell size and a uniform even this linear type of polymeric cell. So that is very important. So we also tune the cell by changing the pH, also important, concentration also important, and also like okay, this is missing the acid water ratio. The water ratio is also important. Well, no data over here. Okay, I'm sorry. I should have some more details data of hydrolysis and the condensation reaction. But I would say the pH acid ratio is very important. Of course, the water ratio is very important. Too much water always give the some very fast reactions, and also temperature also important. So there are many factors.
Professor, thank you for your answer.
Okay, thank you. Ayu, maybe the last question, Dorjana Ratna. Okay.
Thank you for the opportunity before. I think this question is same like the one that you asked you, Professor, but I would like to ask about which one is the best or which one is the most preferably method to make members. Is it the sol gel method or the plasma one? Because
Plasma.
Because as we know, sol gel is needs much solvent and it quite
Are you interested in plasma? Yeah, plasma seems to be very interesting, but soldier, you just soldier is very simple in a sense. Actually, you just have a beaker, okay, put the precursor and water and acid. Okay, you can make the salt, just cold. In the case of the plasma, you need some special equipment. So I think both are acceptable. My feeling is even plasma actually is the ratio of deposition to fabricate a membrane is less than 1%. Of course, the sol gel process, we need a lot of solvent, of course. But even in the plasma, okay, deposition percentage is also less than 1%. So 99% is now exhausted. So, but anyway, it is depend on your research interest.
I was wondering if so the plasma method is still I mean we are still exploring about the plasma method or
yeah. So actually for my laboratory, plasma is a new research area, so we enjoy a lot. But still a lot of area to work on the plasma CBD techniques. Yeah.
Okay. Thank you for your explanations.
Okay, thank you, Ratna. Because Ratna, to be honest, Ratna, Nurjana Ratna is my student. No, she worked in the fabrication of zinc oxide and silica and application in the photocatalytic performance using the gas-phase method. Yes.
Really? Okay. So CBD, you are working also in CBD techniques?
No, Sensei. Electrospray and also using the spray pyrolysis flame.
Okay. Okay.
That's why
you
maybe,
can.
That's why maybe she's curious about the difference between the liquid and the gas phase. I guess.
So so you can apply those kind of spread film or membranes also. Separation membrane also possible.
Okay.
Maybe there's different about my work with your explanation, Sensei. In your explanation, the sol gel was we put the beaker and we pour some solvent. But in my work before is we have to do distillation first to make the sol is stable. So I was curious about that. So I was asking about that too.
Because the precursor is different, Sensei. In the case of
okay.
Inorganic, using the water class as the precursor, that's why we need the pre-treatment before using the convert to the silicic acid, Sensei. Okay.
Yeah. Okay.
Maybe, yeah, maybe Nurjana is interested in studying in Japan, maybe. Perhaps. Okay, because the time is 6:35, so maybe I will terminate the session. Maybe Professor Tsuru have the last speech, Sensei.
Okay. Okay. Thank you very much for participating in this my lecture. Even the early in the morning, I'm a little bit surprised. Your first lecture, first class start from 7 a.m. in Indonesian times. So
Yes.
I believe, you are very hard-working country, hard workers. You can do much achievement in near future. I hope, some of you understand the interest of the membrane technology, especially silica type membranes. Also, my research interest is amorphous types, hoping to be commercialized in future. And then also, if you are interested in coming to Hiroshima, please contact me, okay, by email. It is my pleasure, okay. Yeah, thank you very much for joining today. And then also I'd like to thank Dr. Kusudian for organizing and reorganizing my lecture. Thank you very much.
Okay, thank you very much, Tsuru Sensei. And maybe I will give the time to MC, Miss Anissa.
Okay, thank you very much, Mr. Kusdianto, for guiding our amazing session of lecture. And also, I would like to say a big thank you again for Professor Toshinori Tsuru for the excellent explanation in our lecture today, which certainly expand our knowledge. Okay, now before we close our lecture, I would like to invite all of the participants, as well as our honorable speaker and moderator, to turn on the camera and take a group photo. Okay, once again, for all the participants who have no problems in network or else, please turn on your camera before we start the group photo.
Sasin Sensei, Sasin. Miss Anissa, can you count?
Yeah. Okay, maybe for the first slide, I will count down from 3, 2, 1. Okay, for the next slide. 3, 2, 1. Okay. Maybe because the last slide, there are no participants who turn on the camera. That's all for our group photo, and that is also the end of our agendas today. Once again, I would like to say thank you again for Sensei Toshinori Tsuru for your willingness to reschedule this lecture and give an amazing explanation about silica membranes for all of us. Okay, maybe you could continue your activities. Okay, thank you, Professor.
Sensei, arigatou gozaimasu.
Thank you very much.
Thank you very much, Sensei. Okay, maybe I will end this meeting, Sensei.
Okay, good.
Again, thank you very much, Sensei.
Thank you from me. Okay, thank you very much. See you next time.
See you next time, Sensei. Because I still have the research collaboration with Shimada Sensei. So sometime I visit to Irodai, but due to the pandemic, so maybe 2 years.
Next year or next
maybe,
year. Okay.
Yeah, perhaps next year I can visit Irodai.
Yeah.
Okay, Sensei. Again,
thank you very much. Okay.
Yes,
Thank you. See you. Okay. Bye bye.
Bye.
Okay,